Welcome everyone. In this lesson we're going to be looking at chain rule. So chain rule for kind of these multivariable functions. And there's going to be a few different versions. So let's look at the first one. And I think a good way to start this off is to review our chain rule from Calc 1. So the original chain rule here. So let's write out what that was. So we have our original chain rule going all the way back to Calc 1. And what this said was that if we had y equal to a function of x, and if that function was differentiable, and we had x written as a function of another variable, maybe like t, and that was also differentiable. Well, then we could say something about the derivative of y with respect to this other variable t. So when we look at the chain rule, this is really what we're doing is a kind of a composition. So we had y written as a function of x, and then x was written as a function of t. So kind of indirectly, y was also a function of t. So it made sense to think about, well, how does y change with respect to time? So what is the derivative of y with respect to time? And how the chain rule looked, we would differentiate our function f with respect to x. So we differentiate this function with respect to x just like regular. And then we would multiply by the derivative of x with respect to t. So this is really the derivative of the outer function times the derivative of the inner function. So this was our chain rule that we saw back all the way back in Calc 1. Now we're kind of moving on up to more than one variable. So we have this kind of extended chain rule here, and this is going to be there's going to be other cases that we look at. So we'll see those in a little bit. But we have z equal to a function of x and y, and we're going to make the assumption here that z is a differentiable function in terms of both x and y there. And x is a function of time, and y is a function of time, and both of these are also differentiable functions. Well, if that's the case, then we can view z as a function of time, kind of indirectly, and it's also a differentiable function in terms of t. And the way we can calculate this is with this kind of extended chain rule formula. Looks very similar to the original Calc 1 version here, except now because z has two variables, x and y, there's kind of two parts to our chain rule here. All right, so let's look at what we have here. And the key thing to keep in mind here as we're talking about chain rule is it's a composition of functions. So we have x written as a function of time, we have y written as a function of time, and z is written as a function of x and y. But really, since x depends on time, z also kind of indirectly depends on time as well. So our function z is indirectly a function of t, function of time. And so it makes sense then to think about how does z change as time changes. So what is the derivative of z with respect to time? And the way we're going to calculate that is we're going to do the partial derivative of our function f with respect to x, and then multiply by the derivative of x with respect to time. And then we're going to do the same thing for our y variable. So we'll do the partial derivative of f with respect to y, and then multiply by the derivative of y with respect to t. So when we look at this, a couple things to keep in mind. dz dt, dx dt, and dy dt, these are just classic derivatives. So these are just classic one variable derivatives that we saw all the way back in Calc 1. The new part here is these partial derivatives, df partial f with respect to x and partial f with respect to y. So there's kind of a mix of regular one variable differentiation here, and then we also have these partial derivatives. So we're not going to go into the proof of this chain rule, but if you're interested, I'll leave it for it's in the review video. So kind of a detailed proof, but if you're interested, it's there. So let's try an example. So example 1, we're going to find the derivative of z with respect to t. So again, think of t as time. And we're going to find this derivative when t is equal to 0. So our function z here is x squared times y plus 3x y to the 4th. And again, think of this as a surface that's kind of hovering above our xy plane. And then we also have x written as a function of time and y written as a function of time. So we have x is sine of 2t, and y is equal to cosine of t. All right, so let's see. So what we have here is we're viewing z as a function of time. As it's written, z is a function of x and y, but then x is a function of t and y is a function of t. So indirectly, kind of by a composition of functions, z is also a function of t. So it makes sense to think about the derivative. So let's write down our chain rule formula here, just to kind of get going. So our derivative of z with respect to t is going to be the partial derivative of f with respect to x times the regular derivative of x with respect to t, and then partial derivative of f with respect to y times the regular derivative of y with respect to t. So we kind of have 4 things to calculate here. So let's kind of go through and figure them all out. So let's start with our partial derivative of f with respect to x. So we're going to do the partial derivative of this function. All right, so let's try that out. All right, so we look at this, and we're doing the partial derivative for x. So we're going to differentiate that x squared just like regular, and then the y is a constant multiple. So when we do this, we get 2x times y for the derivative of that first part. And then for the second part, we're going to differentiate 3x y to the 4th. Again, we're treating that y like a constant, so we're just differentiating that x there in the middle. So think of it as just like it differentiates to 1, and then we still have our 3 and our y to the 4th. All right, so that's our partial for f with respect to x. Now, while we're at it, let's do the partial of f with respect to y. All right, so now we're viewing y as our variable. So for the first term here, the y differentiates to 1, and we're left with our constant multiple of x squared. And then in the second part here, the 3x is a constant multiple, so we're going to differentiate that y to the 4th. And when we do that, we get 12x y cubed. All right, so those are our 2 partial derivatives. And we're also going to need, what else? Well, we're going to need our x derivative with respect to time and our y derivative with respect to time. So, well, let's get those going. So our x derivative, our function here is x equal to sine of 2t. So derivative of sine is cosine. We keep the inner function exactly the same, so it stays 2t here. Classic chain rule again. And we have to then multiply by the derivative of what's inside. So derivative of 2t is 2. So our calc 1 chain rule rears its head again. And then we got our function for y. So we got to do our y derivative as well. And this is the derivative of y with respect to time. And derivative of cosine is negative sine. All right, so we have all of the ingredients. So now we just need to kind of put them in our formula here to actually write out what this derivative actually is. And let's do that right down here. So our derivative of z with respect to t is going to be, well, we have our x partial derivative, which we're going to fill in right here. So that'll be 2xy plus 3y to the fourth. And then we're going to, and let's get some parentheses around that. And then we're going to multiply by our time derivative of x. So our time derivative of x, what do we find? We're going to throw that in right next door. And that's going to be our 2 cosine of 2t. And again, let's get some parentheses just for the good practice there. All right, so then we have a plus sign in between, and then we're going to fill in our y terms. So we have our y partial derivative that we're going to fill in. So when we do that, we get x squared plus 12x y cubed. And again, let's get our parentheses around that. And then we're going to multiply by the derivative of y with respect to t. So we'll have our negative sine t down here. All right, so that is our z derivative with respect to t. Now, if we were just trying to find the derivative, we could go a step further. And because we're trying to find the derivative of z with respect to t, if we can do it, it makes sense to try to get this all in terms of t. And the way we would do that is we know what x is in terms of t, and we know what y is in terms of t. So we would fill those in wherever we see an x and a y. So just a little note here. We can fill in x and y to get this function, or to get this derivative, all in terms of t. All right. But we don't need the derivative exactly. We need it at one specific time value here, time 0. So what we can do is we can just kind of plug into the individual pieces. So let's kind of back up. And we know we're trying to find where time is 0 here, our derivative at that specific time. So first of all, we can plug in this time value to figure out what the x and y values are. So at this specific time, if we plug 0 in to our sine of 2t function, that tells us x is 0. And if we plug into our y equation, we get y is equal to 1. And let's kind of do that now. So we can just come down here to our derivative, and we want to evaluate this when t is equal to 0. And when t is equal to 0, we found also that x is equal to 0 and y is equal to 1. So basically, wherever we see a t, we'll plug 0 in. Wherever we see an x, we'll plug 0 in, and wherever we see a y, we'll plug 1 in. So let's see what we get. So for this first part, we're going to get 2 times 0 times 1, so that'll be 0, and then plus 3 times 1 to the 4th. So we're going to get 3. And then for the second piece here, 2 cosine of 2t, well, we're plugging t equals 0 into that, and we get 2 times cosine of 0, which is 1, so we end up with a 2. And then we do the same thing over here. So wherever I see an x, I'm going to plug 0 in, so that's going to be 0, that's going to be 0. And automatically this whole second part's going to be 0 then. But just for the fun, let's plug t equals 0 in to this last part here. We get sine of 0, which is also 0. So we end up with our time derivative here being 6. All right. So it kind of helps to have a little picture of what's going on in this situation. So here's two kind of plots. And in the first plot, we have our x-axis, we have our y-axis here. And what we're plotting is the parametric curve given by x equal to sine of 2t and y equal to cosine t. So this is the parametric curve just plotted on the xy plane here. And at t equals 0, we're actually at this point right up here. The x-coordinate was 0, and we saw the y-coordinate was 1. And so as we let kind of t increase from there, we, again, think of these parametric curves as like a particle that's moving along the curve. We have its full trajectory, but we want to think of the t value as telling us where we are at a specific time. So at time 0, we're at this location. And then as t increases, the particle kind of moves this way around the curve. So we actually get kind of an orientation here, a direction component, how we're moving along the curve. And then eventually, if we let enough time go by, this is a closed curve, so we get back to where we started. All right, so that's just the x and y equations. Now, what happens if we throw that surface equation in? Well, if we do that, let's kind of look at this new version of our surface or of our parametric curve. Now you can kind of see the parametric curve. Here's our, let's see here. We have our x-axis back here. So it kind of extends back there. We have our y-axis, and then our z-axis is pointing up. And the parametric curve in this case is now a three-dimensional parametric curve. X is still the sine of 2t. Y is still the cosine of t. And now we have a third part of our parametric curve, the z part, where we essentially take our surface. So we have our surface plotted here. And what was the equation of our surface? It was z equal to x squared y plus 3x y to the 4th. And we could find the z part of our parametric curve by taking x, plugging it into our z equation, and taking the y value and plugging it into our z equation. So I won't write that out, but that's how we'd get our z component here. And now this gives us our parametric curve that if we kind of look at the shadow of this curve on the xy plane, we would see exactly this shape, this kind of hourglass shape here. But now extending it to 3 dimensions, it's running along the surface. And so in our case, the point that we were looking at was right here, t equals 0. And what we saw is that the derivative of z with respect to t at that point was 6. And so what that's telling us is it was telling us how fast our elevation was changing at that specific moment in time. So we have this particle that's kind of traveling along the curve here, and it's telling us, the derivative is telling us how fast the elevation was changing as our particle was moving. And so we can see that if we kind of look at this, as our particle moves, remember it was kind of taking this way around the hourglass figure. So what we can see here is that at time 0, it starts moving uphill. So for that section, since the height of our particle on our surface is increasing, the derivative in this case would be positive on this section of the parametric curve. And then something happens right at this point. It hits a high point on our curve. So at that point, the derivative is actually 0. So our derivative at that point is equal to 0. It hits a high point, so it momentarily stops increasing the height and just kind of hovering there at that high point. So the derivative is 0. And then after that, it starts to decrease. So the elevation of our particle starts to decrease. And then we hit a low point. So on this section of our parametric curve, the derivative of z with respect to t would be negative. So that's what we're seeing right here, is the height of our particle is decreasing. So the derivative there would be negative. So you want to think of this derivative dz with respect to time as kind of telling us how does our elevation change as we're moving along this parametric curve. All right, so it helps to have a picture like this. And what we're going to be looking at in class next is kind of another version of the chain rule, but this time it'll be where z is a function of x and y, and x and y are also multivariable functions rather than just single variable functions. So we'll look at that in class. We'll see you then. Bye-bye.